Hey, God. So, welcome to our the Scientist podcast, and today is the episode 8. And thank you so much for everyone who has. We are a family of 90 people, so that's the progress in 1.5 months. And for a science community, it's like a big seminar. So that's
Yeah,
very nice.
that's true. Yeah. Yeah.
And we get 200, 300, sometimes 500 views. So that's very nice of people, and people stay in our videos. That's really cool. And every time we try to bring a new story, a new topic about science and try to understand why we should all be interested in science. And of course, I'm joined with Dr. Mrityunjay Sharma. And today our guest is Dr. John Carlton, who is from UK and now in UKY. So, so let's see what he has to tell us about today. And thank you first so much for accepting our uh, accepting and please tell me about yourself.
Okay, great. Thanks, guys. Yeah, I'm really happy to be here. So yeah, I have come from the United Kingdom, UK, and I'm currently a postdoc in theoretical physics at the University of Kentucky. I did my undergraduate and master's in the United Kingdom at the University of Birmingham, and then I went on to do my PhD at King's College London, in London, and then I've moved across to the US in the last few months to start this postdoc here. It's been a very short position. I'm about to go back to the UK, and then I'm taking up another research position in Germany in the new year, which is very exciting. So my research has mostly focused on dark matter, which I think is the topic we're going to discuss today. I would consider myself a theorist, but I sort of started in a kind of more experimental program, which saw me doing a lot more kind of lab-based stuff. But I kind of decided by the time it was ready to apply for PhDs, it wasn't really for me, and I transitioned more into doing theoretical stuff. And now I just work on, computers and simulations, and I don't get bogged down in the lab based details, but I have great respect for those who do. And I kind of work in between the two. So I'd call myself a phenomenologist,
Hmm.
which means that I'm looking for kind of the theory that we can apply to experiments, and kind of filling the gap between theorists and experimentalists so we can really optimize what future experiments are going to be able to do and see. Trying to come up with new kind of targets for these experiments and new kind of ideas that we can apply uh, to physics more broadly.
Oh.
Yeah.
So, John, I mean, I think obviously we'll talk about dark matter and a little about your research, but I think before going into that, would love to know a little about how did this whole journey started? Like, when you were,
Mm.
let's say, when you were a kid, right? Like, what was that one moment or what was that trigger, that pushed you towards physics, right?
Yeah.
And then, what actually pushed you towards theoretical physics and then obviously you know dark matter finally.
Mm-hmm.
I think that's something that we would love to know a little. Yeah.
Absolutely, yeah. So I feel very lucky in a way because I've always been interested in physics of some kind. Yeah, like even in the first few years of school, I instantly knew I liked science. I knew I kind of wanted to follow this path, and I think most people don't have that kind of drive. I think it's also lucky that, school kind of pushes you academically in a certain direction. And a lot of people feel like I don't like school, so I don't want to do something related to academics in my future. But I feel very lucky that I things aligned in such a way that very nice to see meow there. That I, got to pursue kind of what I was interested in, and that naturally led me to kind of going through the, university and the academic system.
Mhm.
As for physics, it was well, so my father did a degree in physics,
Hmm.
and he was always very interested in it and would kind of imparted that onto me, I think, a bit. Um, but also, it's kind of in some ways, it's what I've grounded my life in. It
Mhm.
kind of gives me purpose.
Mhm.
Uh, I was a very kind of maybe introspective child in that sense, is that I liked philosophy and I liked science because it tried to answer fundamental questions about things. And that's really kind of what drove me towards particle physics and theoretical physics specifically, is that it tries to describe, the lowest level of reality that we can access experimentally. It's trying to really get at some of those deep fundamental questions. And those are the things that have always interested me about the start of the universe, what's, everything made of. And
Mm,
maybe it can't answer the why questions, like, why are we here? The nature of God or whatever else. Maybe the
mm,
deeper questions we have to leave to religion and philosophy. But I think it at least helps inform us a bit more and tries to answer some of those questions, even if the physics itself seems kind of removed from your daily life. It's still something that I find is a nice foundation to fall back on.
mm.
Um, yeah, and I kind of realized this more and more as I was going through like high school, and I knew I wanted to do physics, and then particle physics was kind of like, okay,
Was
this.
there like a particular moment in your high school when you were like, oh, I think physics is it for me? Or like, maybe a
Yeah.
conversation with your father, right? Like when he was maybe talking about some physics phenomenon, maybe you saw like those what do you call it? The aurora lights, right?
Mm,
And you were like,
mm, mm.
hey, what's happening there? Like, was there any moment that was like, okay, I mean, maybe this is what I want to do.
Yeah, it's hard to kind of pin it down to just one thing. I
Hmm.
think I think it was a slow kind of accumulation of all those interesting conversations. It was always, space is the first thing that a kid like gets interested in, right? It's like you see,
Absolutely.
yeah, you,
Yeah.
you see, I don't know, footage of the moon landings, you see whatever spaceships going into the sky, and that kind of captures the imagination immediately. So
Hmm.
originally I thought I want to study, maybe I want to be an astronaut, maybe I want to study the stars and things like that. But
Yeah.
then it kind of goes a level deeper when you think about, okay, so this is space, and this is, where did it all come from? How did the universe start? What's all of this kind of cosmology that we people say the universe is this many billion years old? How do we know that? All of these kind of questions kind of built up over time, and that's kind of what pushed me to pursuing these kind of what I would consider quite a fundamental level of physics. I think my attitude has kind of shifted. In some ways, it's kind of a childish view to think that one study of one science is going to give you kind of all of the answers because there's so much depth in biology and chemistry and everything else that we study. But I really like that it kind of all comes together in this one picture to try and make sense of stuff we see in the world. Um, in terms of like high school, I had some great physics teachers as well, and they were always super encouraging. Not many people wanted to do physics, like go on to do a physics degree and then go on to do like academia, but because I sort of had expressed that interest, I had some really nice teachers that would try and foster that interest in me. Um, and yeah, I think it was conversations with them, with my family, that really kind of gradually pushed me in this direction. And I can't say that there was one singular inspiration, but
Hmm.
I just feel very lucky that I've managed to sort of pursue this path and been kind of guided there by all sorts of forces in my life.
Is
Uh,
there is there anything like I know that you are into particle physics and you guys are into, hey, we want to know the origin of the universe. Get that, right? But is there anything else that fascinates you? That is there anything that you feel like that, oh, come on, I can't find an answer to that. Is there
Mm.
something like that as well?
You mean something like a question that I don't think could be answered by physics, or
Uh,
something I
yeah,
wish
like
I had
some
studied as well, or
yeah, something you feel, I mean, something that fascinates you, but you
mm,
don't have an answer to it yet.
yeah, I guess I think maybe in the realms of biology and chemistry, we kind of have way more interesting stuff that applies to our daily life in terms of maybe like neuroscience. So exactly what the nature of the brain is and where consciousness comes from and things like this. Stuff I really wish I knew more about. I think there's a really interesting question in that neuroscience attempts to answer. I don't know if it can, in the same way that I don't know if physics can really tell you, the purpose of the universe. I don't know if a neuroscientist can actually tell you where consciousness comes from, where like our minds come from in a kind of scientific material way. So it's very interesting to try and put those pieces together and try and answer that question. So that's something kind of I wish I'd studied more.
Hmm.
Um, I kind of, I think if you study any topic enough, it's
Hmm.
interesting, right?
Yeah.
And
no,
that's what I
that's
found.
cool.
Yeah,
Yeah, no,
yeah.
I think you are perfectly right that if you try to study anything like for multiple years or many years, or you try to become an expert in it, at least
Yeah.
you think it's the best topic, and it's very fun to study. For example, I can't understand
I
physics,
mean, you should
obviously.
think it, and
Uh,
also your funders should think it, right?
yes, yes, yeah, yeah. Yeah, I am weak in both of them, so both of these things. So that's fantastic. So coming back to your topic,
Mm,
so you try to understand dark matter.
yes,
Now,
exactly.
I don't understand anything about dark matter. I don't even know what is the dark matter.
That makes the two of
So
us.
so
Well, this is excellent. This is a great opportunity.
so,
So, I
so
mean,
yeah. So sorry. What is dark matter, and why is dark matter? Like why? Why do we need to
why
know?
do we
Like
care? Yeah, yeah.
what do we need to
Um,
know?
So, okay, so dark matter is kind of a buzzword, right? You've probably heard it before,
Hmm.
um, in some context, and I think there's some, I don't know, sometimes when I go online, if I go on Reddit or wherever, people are talking about science. Sometimes someone will say dark matter, and people will respond like, "Oh, that's not real. No one's found it. It's a hoax or whatever." And I think people have some interesting ideas. So, maybe to start, what do you guys think is dark matter? And then I can sort of expand on that picture. What
I
do you think of? What do you think of?
I don't think about dark matter.
Same,
Uh,
man. Like,
no, so it's like I don't know. I have to like guess weird some particles around this space that we don't know, and that it's like a group of things that it's like any moving objects in this space. That is
Mm.
also a thing that we just don't know. It just absorbs all energy. I don't know, something like
Yeah,
that.
yeah, yeah, yeah. I mean, that's a good start. So it's like something in space that we can't see directly. Um, and contrary to what some people might say, we have an overwhelming amount of evidence that it actually exists. We don't know what its like fundamental nature is, but all of our observations of, galaxies, of the universe, the structure of the universe and galaxy clusters and everything leads us to conclude that there must be some extra missing mass that we can't account for in the usual kind of model of particles and interactions that we currently have. So some of the earliest evidence comes from looking at the motion of galaxy clusters, um, and sort of noticing that as they move, you can sort of measure how much optical matter there is. So stuff that gives off light, most of it is stars and dust. It gives off light that we can see and measure with telescopes on Earth. But what we find is that the motion, when we model it, isn't really accounted for by just the luminous, matter that we can see. One of this also applies in all sorts of other places, like galaxy rotation curves is probably the best kind of first piece of evidence, and it's the most intuitive. So hopefully I can construct the argument. So if you look at a single galaxy, like the Milky Way, it's like this big spirally thing, and we have a supermassive black hole in the middle and a very dense concentration of mass. And effectively, everything in the galaxy, our solar system included, is orbiting that big center of mass. So when you look at other galaxies, and you see that they're structured the same way, you would expect that because we know gravity we can model as an inverse square law, it falls off with distance, in strength. The further out a star is from the center of the galaxy, you'd expect that it's being pulled on less strongly. You'd expect that it orbits at a slower rate
hmm.
to sort of have a stable orbit. What we really find is that when you look at basically any galaxy, if you track the velocity of stars as a function of the radius from the center, all of the stars, all of the solar systems are moving roughly constant,
Hmm.
roughly with the same speed. There's no fall off with the strength of gravity. Instead, it's like they're all moving at once. And a really good explanation for this is there's actually some extra missing matter that is kind of surrounding the whole galaxy. We call this a halo, a dark matter halo. And because there's all this extra matter, 5 times the amount of matter that's just in the ordinary galaxy, it is kind of causing everything to co-rotate with it in this big sort of bubble.
Hmm.
Um, yeah, and we see that with every galaxy, and you can't explain it. Some people try and explain it with like changing the force of gravity with distance, but and that can work. But then we have many, many other pieces of evidence that are much stronger. But I think that's a nice kind of start intuitively to think about where this matter is. So it's like in the galaxy, surrounding all of the ordinary luminous matter, um, and we're trying to figure out what it is. So, it could be in this room, it could be, all around us, or it might not be. But
So,
we're trying to sort of come up with ways of measuring it directly.
so when you said
Hmm.
loss of mass from where? Like, where was this mass before?
Good. I mean, so the best kind of uh, evidence we have comes from very, very early measurements of the universe. So just like all of the ordinary matter, so our model of the universe starts with the Big Bang. There's a rapid expansion and cooling. Um, there's all of this energy that effectively condenses into particles. But for a long time, or for at least the initial stages of the universe, it's far too energetic for the sort of constituents of a nucleus to condense into actual elements that we know and love that would then go on to form kind of hydrogen and helium and gases and dust that would then condense into galaxies and solar systems, etc. But what we know is that in the very early universe, the structure of galaxies, the structure of the whole like network of galaxies we see in the universe today, must have been seeded by something that wasn't sort of stuck in this strong coupling regime at the start, where all of the matter couldn't condense to form galaxies, couldn't condense to form, you know, atoms and nuclei.
Hmm.
So we suspect that there was some dark matter that was also produced from this initial burst of energy in the universe that then doesn't have all of these collisions. We call it collisionless. It doesn't have strong interactions with the other particles, so it doesn't, it doesn't matter that it's really hot and it can't condense.
Hmm.
Instead, it can start collapsing into these galaxy halos first,
Hmm.
well before the matter can then condense and form, the usual stuff we think about. And so when it finally, the universe expands enough and cools enough that ordinary matter can form, ordinary galactic material can form, then there are all of these dark matter wells that are spread out across the galaxy that the ordinary matter collapses into, and it sort of seeds all of the structure we see today. And that is the best kind of model we have to explain why galaxies and galaxy clusters look the way they do to us right now with telescopes.
Oh, interesting. And like let's say one fine day someone actually discovers what dark
Mm.
matter is, right? How will it change our world? Like what will happen then?
It's a good question. So it's the standard model of particles that we have is really, really good at making predictions about most things.
Hmm.
But it's quite worrying that then there must be some extra stuff that
Hmm.
can't, doesn't fit into the model. So that's the thing. We don't really know. We can explain its dark matter's gravitational behavior, but we have no idea what its actual like fundamental particle properties are if it fits into the model of the rest of the stuff. But we can imagine, it might be some really useful stuff to
Hmm.
have access to. I mean, a lot of physics advancements in this sense are about kind of advancing our use of technology or
Yeah.
advancing the way we can manipulate matter on some very, small level. Dark
Yeah.
matter itself may have unintended effects and consequences on a kind of fundamental level that will better improve our sort of technology, especially on kind of very, very small scales. On the other hand, it might not have such a big impact on kind of
Hmm.
day-to-day stuff. But either way, it's going to explain a lot about kind of the mysteries of the universe. It's one of the big, ones because we have these models, they predict things very well, and
Yeah.
yet they cannot explain, on a deeper physics level. It's like, why, what could this, be explained by? What is this dark matter? Um, yeah, it's still one of the biggest mysteries that we have.
Yeah.
I think we had a guest who talked about the quantum mechanics.
Mm.
And when you talk about the dark matter that is from the like back of the universe, what are like the similarity or dissimilarity? Do you use quantum mechanics, the quantum hypothesis ideas to understand dark matter?
Yeah, exactly. So the really cool thing about dark matter is that when you study it in its entirety, you're going across many different sort of regimes of physics. So because we don't know what mass it is, it could have it could have a mass that is, if we imagine it's a single new particle,
Hmm.
that particle's mass could be something similar to the protons and neutrons of, ordinary atoms. It could be much heavier. It could be a really, big, heavy thing, and it starts to act less like a particle and more like a macroscopic object. And there's even people who say that small black holes, could be dark matter. Potentially, in the start of the universe, black holes could have collapsed from some initial perturbation of density that then, seeded all of this structure later on. Um, and these could be like solar mass objects, really heavy stuff. On the other hand, it could be, these sort of more intermediate particles, or it could be even lighter. And you start to get all sorts of interesting sort of quantum effects the lighter the particle is. So if it's these really big, heavy things, it acts like almost like a planet or a star. And we can try and find it through kind of classical physics in a way. But anything else to try and fit it into our sort of particle picture of the universe, we need that kind of quantum description to really like fit it in. And that's the thing. It's like we have really good quantum mechanics as it is, really
Hmm.
explains everything that we can see to some extent,
Hmm.
but it doesn't explain dark matter. So we need to try and integrate it with our picture, and we need to have a kind of quantum description of it if we want to really explain it properly.
I think in terms of, talking about the description of dark matter and talking about, small scale, you've spent a good time, right, while doing your thesis on atom, what do you call it, atom interferometer,
That's
right?
right, atom interferometry. Yeah,
Would love to know a little more about that. Like, what were you
absolutely.
doing with that, and
Yeah,
how does it, because I think it has something to do with rats as well, right?
yeah. We can get into
And I
that
was
for sure.
when I was reading about your thesis, right, I
It's
was really
amazing.
fascinated that okay, we are talking about dark matter, but where is this rat coming from?
Mm,
So people who may be
Yes,
watching this, right, why don't you
yes.
quickly explain what this is
absolutely.
about?
Yeah.
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 So yeah. So my actual research,
Mhm.
all of this dark matter stuff kind of comes before. It's like the background.
Yeah.
But as I mentioned at the start, I think of myself as more of a phenomenologist. So I like to work with experiments to try and think about what they can see.
Mhm.
So there's this new class of experiments that have been in development for the last few decades, but are now going to try and detect dark matter directly. And they're called atom interferometers. An interferometer is just any experiment that uses interference.
Mhm.
So we can think about, waves interfering constructively, destructively. You think about light, you can split a beam of light and sort of
Yeah.
interfere it to try and make a measurement of things. Atom interferometers do the same thing, but we think about atoms as waves that we then split and interfere. So you can, in quantum mechanics, treat an atom or a cloud of atoms as being in a superposition of two states. So it's almost like it's in two places at once. You split it across two different paths, and then they re-interfere and they make a measurement. All that's to say is that these are kind of using principles of quantum mechanics
Mhm.
to make measurements of quantum effects. And
Mhm.
if dark matter is kind of one of a new particle, it may have a small, weak interaction, with the rest of the quantum world
Yeah.
that we can then make a measurement with these detectors.
Mhm.
So these are really exciting technology because they're very sensitive to all sorts of effects. They're sensitive to accelerations. They're sensitive to kind of shifts in quantum energy levels from
Mhm.
maybe from dark matter. They potentially can detect gravitational waves and other kind of interesting stuff. But because, the acceleration thing is key, because it means any matter in the environment of the experiment is
Yeah.
potentially going to be a signal. And many of those things are not things you necessarily want to measure. So one of my first projects during my PhD was thinking, okay, in a few years, we're going to hopefully have a 10-meter version of this experiment. So you're sort of launching atoms into the air,
Mm.
you're measuring them with lasers and trying to infer this information. But it's going to be located in a public university building,
Mm.
in a
Yeah.
basement. There's going to be lots of people walking past. There's going to be cars on the road outside. There's
Yeah.
potentially going to be rats and other rodents and things in the sewers underneath. And
Yeah.
because it's all mass,
Yeah.
right? And these experiments are so precise and so sensitive.
Hmm.
Any sort of change in the local gravity
Hmm.
from any massive object is
Hmm.
going to sort of have a small force that acts on the atoms,
Hmm.
shifts them very slightly,
Hmm.
and is going to potentially be noise when we're trying to look for dark matter. And that's where the rats come in.
Oh, wonderful. Sorry, I will ask just one more question because
Sure.
I think because you're talking about acceleration, two questions actually. Sorry. First is how expensive are these interferometers, right?
Mm.
And second question is if they are so sensitive, can we also use them, right, to predict, let's say, natural disasters like earthquakes, right? Because is it possible to predict a tectonic shift way before than before it is happening, right?
Mm.
And is it or is it something that's already happening and I don't know about it?
Sure, sure. So great questions. So in terms of the cost, I'm not in charge of the money, so I can't say for sure. But these are,
Expensive.
relatively, yeah,
Expensive is the word.
yeah,
Expensive.
expensive. Um, I mean, there's a lot of interest, there's a lot of investment in this technology. So,
Hmm.
um, I think it's relatively cheap in science terms to build a small version of this.
Hmm.
But to develop the kind of longer and bigger versions of these
Hmm.
is new stuff, right? It's going to require experimentalists to do a lot of research and development to actually, take what is effectively a very small tabletop quantum thing and
Hmm.
try and extend it over very, very long space scales. And we're mostly there with one version of our experiment. A lot of these are currently being built for physics applications, and they're costing, millions of dollars. Maybe
Yeah.
small in as a slice of the total, government spending, but it's obviously not something anyone can just set up in their home laboratory. Um, but no, it's a really, really good point to think about what else they can be used for. And I think that's why, hopefully, that these things are going to be funded. And part of my other research has been looking into kind of more environmental effects
Yeah.
that can be measured by these experiments. So you're right, accelerations
Yeah.
are everywhere.
I mean, thinking about it, I just realized that we can also like there can also be predictions of, change in air pressure, right?
Yes,
Which
absolutely.
is a biggest cause of, destruction. At least I've heard like in the US, in India, like any coastal area, right? There are always typhoons and cyclones. And if it is not that expensive, like something that's, if it is
Mm.
at a fraction of what a government can build, then I think it can change a lot of lives, I feel, right? At least
Yeah,
provide that preparedness, I feel.
that's the hope because these things are so sensitive that
Yeah,
when they are built and when it's easy to reproduce them and make many of them,
yeah.
they're effectively better versions of existing seismometers and
Mm.
atmospheric pressure monitors because they just couple to any acceleration. So changes in air pressure, like you said, one of our main noise sources is going to be from seismic waves. So
Mm.
we've done a lot of studies to think about, as a seismic wave passes along the Earth, it's displacing the ground very slightly, which changes a very small amount the gravity that you feel,
Yeah,
that the atoms are feeling when making a measurement. And one of the biggest, pushes and drivers to improve seismometer technology is early warning earthquake detection systems. So there's
yeah,
all sorts of, when an earthquake happens or when a tsunami happens, when like these big cataclysmic natural disasters happen,
yeah.
there's an outpouring of energy that spreads across the earth in waves. And a lot of it, the stuff that, would reach us first is are waves that are very, very, very small in amplitude. We
Yeah.
only start to, it builds up over time. There's some early waves that are smaller, kind of less significant effects, and then you get slightly bigger ones, and then you get the really big disruptive waves that are shaking the earth and causing all of the damage and harm to people. So if we can build really sensitive instruments,
Yeah.
and maybe these atom interferometers are going to be that instrument, then you potentially gain, minutes rather than seconds to be able to warn people, to be able to react, and hopefully save lives. So I think that's a really exciting thing. Also, just in general for Earth sciences, so for monitoring the atmosphere, for monitoring climate change and all of these effects,
Yeah.
the better sensors we have, the better models we can build, the more we understand these effects, and the more that kind of informs research. So
Yeah.
it's really nice being a theoretical physicist mostly that I
Mm.
get to contribute to something that will hopefully, introduce a really useful, helpful technology into the world, which I love doing.
I,
Absolutely.
I think in last 25 minutes, what I learned that your work involves like dark matter, quantum physics, quantum gravity, string theory, 100%. So how smart you have to be to understand these kind of things, and
Oh,
to
wow.
how smart you have to be.
Yeah, I mean, just to also like put it from a point of view, let's say if there is a high school student,
Mm,
right?
Yeah.
Or if there is a young undergrad student who wants to get into, what you are doing, I mean, how smart they have to be, what do they have to do,
yeah,
to be able to do what you are doing, right?
yeah.
So, yeah.
No, it's a good question. I think I'm a big believer that you don't have to be a genius. You don't have to be really, really smart to be able to do science and do physics and whatever else it is. You know, to get to my point, I didn't know all of this stuff to start with. It takes a long time. You do, college, university for multiple years, maybe grad school for even longer. And if you worked at any job for that long, you become pretty good at doing it. And that's kind of what physics is to me. Um, you know, it I think if you have the drive and motivation, obviously unfortunately, you need to be able to get the grades. So you need to be able to like be motivated enough and focused enough to be able to get into a university and progress through. But it
Yeah.
doesn't have to be, the best university in the world. It doesn't have to be the most prestigious kind of research that you start doing, because you can always work your way up, which I love. Academia in general is a very competitive environment. So once you get here, it is tough. But again, it's almost self-selecting in a way because you have to be driven and motivated in the subject to be able to pursue it. But I don't think you have to be super smart. I think everyone has their own kind of intelligence. It's hard to say exactly what a good academic makes, but I think anyone who has the motivation to study a subject can make it very far. Um, that's what I like to think. I get
Or you
when I tell
or you
people
can
I
get
do.
lucky.
Well, that's true. There's a lot of luck involved.
And there
Suppose
is
you
a lot
start
of
an
luck
experiment.
involved.
Suppose you start an experiment and you have a grand hypothesis, and the experiment doesn't
That's
fail.
true. That's true.
You're like, yes.
But no, it's a good point. Research is a lot of trial and error. It's a lot of getting things wrong and failure. But that's kind of part of it. And maybe you get lucky and you get a Nobel Prize first time, but that's probably not going to happen.
I think what one thing that I have learned, like having known so many PhDs and academics, it's the persistence, right? I mean, you can be
Yes.
good at it, you can be bad at it, but you got to be persistent about it. I mean, there are going to be rough days, ups and downs, and you'll have all those days, but you just have to go in, work on your hypothesis day in and day out, and see what happens, right? You may get an award, you may not. I mean, that's why academia is also a little, it's not everyone's cup of tea, I feel.
Mm.
It is tough, right? Because you may not be able to solve or understand what you want to do, but that's the fun, right?
Yes,
Of that.
exactly.
And
Yeah.
and and you moved from UK to Lexington, USA for a couple of months. Did you get like we get cultural shock here, obviously, for obvious reasons, because
We
our
we
language
do.
It's
Yeah,
English.
yeah.
I'm sure there are shocks.
I know. No, but like for us, we change our language, food.
Yeah.
Mm.
We change like almost everything, and we literally cross 10,000 miles to come
Uh,
here. For you, how big of a cultural shock for you it was, and how big it's gonna be when you move back to Germany in January?
Abhilash, before John answers this, I
Yeah.
think the language shock is something that I'm sure John is also facing.
Yeah.
Yeah, it's a good point. I don't know. I don't want to say, I feel very, I'm very privileged in a way because I have been, I didn't have to learn a new language mostly. And I didn't have to, I kind of knew what I was walking into to some extent. I feel like I guess, you grow up watching so many US movies and
Yeah,
TV
that
shows and
helps.
stuff. I kind of knew what was going to happen. And academia is a very friendly environment. It's lovely to meet other people who are also, from other countries, and therefore, it's easy to feel accepted. There are a few cultural shocks. It took me a long time to work out, where everything was in the grocery store and the equivalent things that I'm used to buying. But in reality, I don't think I faced that many hardships, which I'm very thankful for. Um, yeah, Germany, I think. I've been to Germany a few times before. It's going to be maybe different working there. I think that's the other thing. It's quite different being a tourist and then having to deal with all of the bureaucracy and the admin that comes with trying to, work in a foreign country. That was probably the thing I was expecting the least, and it can be very frustrating at times. Um, but no, I think that's one of the great perks of this job is being able to travel a lot and work in other places and hopefully be in demand enough that that continues. Um, so yeah, no, I feel very lucky.
No, that's really cool. Any thoughts, Mrityunjay?
No, I think
Uh,
it's been fun talking to John. I think I'm really happy. I got to know, like, I think I'm always excited about these conversations because I always get to know something new, right? In our last conversation, we got to know about, how the grasslands of Assam in India. And now in this conversation, I got to know about these atom in interferometers, right? They are important in their own ways for the world. And yeah, and thank you, John. I mean, it was such a wonderful conversation. And I'm looking forward to, know more in future,
Mm,
when you are in Germany, when you're doing some wonderful groundbreaking research. Would love to, maybe sit down and have another conversation in future. Yeah.
absolutely. No, thanks so much. It's been really fun.
so we ask our guest at the end always to say something to new upcoming researchers about or motivate them about science, and
Mm.
normally in their native language. So whatever your native language is, how would I know? How, how
The
would we know?
mother of all languages.
Yes. Yeah. So if you wanna give them some suggestion or some motivational statement, like couple of lines, like why it is necessary, why science is necessary.
Okay. Yeah. So in English, um, science is a really important tool. It really informs every other part of our day-to-day lives. And being able to be part of it is a really exciting venture. It takes persistence, as we've said. But once you're there, it's such a gratifying job. It really, to me, it really gives purpose to what I do every day, to hopefully see some impact in the future. And even if those impacts aren't, right in front of you, so much of science that's been done has unintended consequences in every part of life, and ultimately hopes to try and make the world a better place, which is
Yeah.
which is what I love doing.
Oh, that was incredible. Thank you so much. And I hope you enjoyed, and I hope you share this with your friends. And I don't know if it's your first podcast or you have done many. I don't know about that. Uh,
Well, it's first of
but
this kind for sure, yeah.
okay. So that's nice. So we are privileged that we get such a wonderful guest all the time. So those who are listening to this conversation, please like, share, and subscribe, and share with your friends, and also share people with us so that we can talk to them and understand their research. So thank you so much. Until next time.
Thank
Bye bye.
you.